Hello students, welcome back again. So now we are moving into session 4. Sessions 1 to 3, they basically covered the devices, analyzing the devices for its performance, how to bias these devices. So what are the devices that we have studied so far? Right, we started with JFETs, then we went on to the two types of MOSFETs which we call as depletion MOSFETs and enhancement MOSFETs. Then we said, okay, how to bias these circuits. So that is true. Now what next? After doing all that, is it only amplifiers where these FETs are used, or are there any other applications for these FETs? Like so far, whenever we try to explain anything, we went on saying in case of amplification, transfer characteristics, larger VGS, larger ID, transfer from VGS to ID, and so on and so forth. So let us now see that amplifier is just one of the applications where it is used. There are many more applications where you are going to use these FETs. We are going to concentrate more on JFETs as far as applications are concerned, but equally we also use the enhancement and depletion MOSFETs. Now what is in store now for this particular session? We are going to see where these FETs are used apart from just the amplifiers that we've been seeing so far. And at the end of it, we also touch upon a very interesting, you can say, a circuit or type of architectures wherein we use both both NMOS, that is N-type MOSFET, as well as P-type MOSFET in a single circuit. Because so far we've been seeing only what? Either an N-type circuit or a P-type. So this is a very interesting circuit that we'll study, which are called as CMOS devices. So C would stand for complementary metal oxide semiconductor devices, which would mean you have both the P-type as well as the N-type devices. So let's quickly run through what can be the possible application scenario. We are listing here at least 6 applications which we are going to run through with some sample circuits using JFETs. Which are those? We start with the amplifiers, move on to analog switch, multiplexers, current limiters, voltage variable resistors, and finally oscillators. Now there are many terms over here which may not be known well to you, which are essentially covered in what we call as the digital portion of this particular course. But still, let's try our best and try and understand what these mean and then see the example. Now coming to amplifiers, that we already been seeing that okay, just because of very high input impedance, because of zero gate current, we said FETs are most suited for low noise amplifiers. Okay, so what are these low noise amplifiers? That means what? I would not like my input signal, okay, which is applied to the amplifier to be loaded by this particular impedance. So higher the input impedance for any circuit, better it is, so that I will not load the input source, thereby ensuring that I have a better amplification and I have less noise, less harmonics in the output. Because usually you would only like to amplify one part, you also end up amplifying the noise also, which you would like to avoid. Now talking of amplifiers, is amplifier just one all and everything all? No. You do have many types of amplifiers. In some cases we also have something called as unity gain amplifiers. Now many of us may be wondering, why would I just choose an amplifier whose gain is unity? In the sense, if I apply a signal of 10 millivolts, I'll get an output signal of 10 millivolts. Then why would I use it? The other name for that type of amplifier is called as a buffer, which are essentially implemented using what we call as common drain configurations. In the sense, common drain techniques. If you connect the input and output in such a way that drain is common between the input as well as output, you end up getting a buffer configuration. Then what is the advantage of this buffer? Even though the voltage is not enhanced or amplified, you do have amplification of current. Okay, or you can also say there is an impedance transformation from high impedance to low impedance. So in essence, buffers can also be called as isolating devices. In the sense, it prevents the input to be loaded by another device on the output. You just pack a buffer in between. This buffer will isolate the input from the output, thereby ensuring a good operation for your circuit. Moving on then, what could be a possible circuit for an analog switch, which we are now showing it on your screen. So this particular circuit uses a JFET, right? Now can you tell me whether it's a P type or a N type JFET? Okay, so the arrow mark going into the gate would mean it is a N type JFET or N channel JFET. Now how is the circuit configuration? You have the voltage source, okay, you have the power supply here connecting the drain resistance to the drain, and then we have the drain here, we have the source here, and we have the gate here. Okay, so this being the case, now how is it that you are going to operate it as a switch? So when will this device be turned on? This device will only be turned on if VGS is allowed to be 0, right? You remember, in case of a JFET, if VGS is 0, means what? I have not done any connection over here, like my switch is open. So if VGS is 0, then this device is going to be working, or it's going to be on, or in other words, a certain current ID will flow, and thereby it is going to drive an output device. Okay, but whenever you want to turn this off, okay, how do you turn off a JFET? You turn off a JFET by applying a negative voltage at its gate. Okay, so you already have a negative voltage here, only thing is it is not in the circuit. So whenever you want to turn it off, all you have to do is make this switch on, which will connect this negative bias to the gate, thereby pinching off the region, and eventually it can cut off the current. And this is what is called as a analog switch. That means you can turn off or turn on. And the question you may ask is, so if that is the case, why don't I directly use a switch? Why do I need this entire circuit for JFET and so on? Again, remember, it does provide what we call as isolation. There is a transformation of impedance from the input to the output. Now this output is, this particular device is not going to load the input here. So that is how we do the application of JFET as an analog switch. Okay, so let's move on then to the next application. So what is this next application? Next application is called as a multiplexer. Now for many of you, this could be a new term, in the sense I do not know what a multiplexer is. So in that case, let me start by telling what a multiplexer is. Typically a multiplexer is something which takes multiple inputs and channelize it to just one output. For example, I'll give an example here. I am coming at an intersection wherein I am having 5 roads converging onto one place and then maybe leading into the airport terminal. Okay, so at any point of time, can I handle all the 5 lanes of traffic into one lane? Possibly not. So what I do is, I allow one lane at a time to go. Once this guy is done, then I go to the next lane, next lane. So turn by turn, I am going to allow one of these 5 to enter that path to the airport. So this we typically call as a 5:1. That means what? I can choose only one among any of these 5. But remember, I can only choose one at a time. So that is essentially what a multiplexer does. You can have many signals coming at the input. I can only choose which one I want and send it to the output. That typically is a requirement for many cases. Okay, so this is how the circuit looks like. So let us say I am having multiple inputs here, V in 1, V in 2, and I am showing multiple sort of inputs here to all the way it goes up to V in N. That means there are N number of inputs to this circuit, but how many outputs then? The only output is this. Does that mean all these devices will go, all the signals will go to the output? It can't possibly go. At the most I can allow V in to go to the output, or I can allow V in 2, or I can allow V in 3. Now how do I ensure that? So all I have to do is, suppose I want to allow only V in 1 to reach the output, what do I do is, at the control input for all the other JFETs, I simply apply a large negative voltage. What does that do? It cuts off my JFET. So once all these JFETs are cut off, now these V in 2 to V in N, they are all isolated from the output. They cannot go and reach the output. Okay, while I only turn V in to to the output how? By giving a 0 voltage or not giving any voltage, you can say, at the control input 1. By doing so, what do I ensure? I ensure that this device is on. So if this device is on, the signal over here, it has a path to reach the output, while all other devices are what we call as tri-stated, or they are in high impedance state. So this is a very simple configuration of using a multiplexer by using just one device. As we go down the line, let us say you're going to study digital logic circuits going down the line in this particular syllabus, you will observe to do a multiplexer you need many transmission gates. Okay, so that's much more complex algorithm. You use NAND gates, you use AND gates, inverters and so on. But here you see here very simple, just one device for each line, so it becomes a very easy implementation and a versatile implementation as far as multiplexers is concerned. So we call this as N:1 multiplexer. By choosing only one input at a time, disabling all the other inputs, I achieve this particular operation very easily. So 2 applications done. So let's move on then to the next one. So the next one has the JFET as a current limiter. Now again, I would like to highlight a bit about what do we mean by a current limiter. I think in all our homes where we stay, we do have what we call as MCBs, right? We have the MCBs. So what do those MCBs mean? It's what is the full form of an MCB? Yes, it's a miniature circuit breaker. So what does an MCB basically do? Let us say I have a MCB of rating of 20 amperes. So as long as the current that is flowing through the MCB is less than or equal to 20 amperes, it will allow that current to flow. The moment the current is flowing beyond 20 amperes, it is going to trip or disconnect that circuit, thereby protecting all your devices. The same thing is also required in many of the electronic circuits. What happens? We do not want the drain current, or we do not want the current to go beyond a point, thereby damaging all the devices. We already seen what avalanche effect does. So I would not like to go on stage where it reaches the avalanche condition. I would like to limit my current much before that. So how do I do that? A very simple approach. This is a configuration that we are showing here on the slide. If you can observe very carefully here, so this is how the connection is done. So this is simple N-type JFET. What we have is, we have the gate terminal and the source terminal shorted. So what does that ensure? That ensures that my VGS is always equal to 0 volts. So if VGS is 0 volts for a JFET, can it be turned off at any point of time? No, right? Then what are you saying? Okay, let me understand that properly. So let me draw the curve for the transfer curve, which is basically VDS versus ID. Now if VGS is 0, this is a type of curve that I possibly have. Okay, this is for VGS equal to 0 volts. Now as and when my VGS becomes more negative, my current starts dropping. I have a lesser curve. Now initially, let us say my current that is flowing in this circuit is around 2 milliamperes. Okay, so let us say I will be here somewhere here. So at 2 milliamperes, so I will be somewhere here. Now what happens? Because of some eventuality in the circuit, a large current rushes into it. Remember, this current is flowing to the circuit which is beyond. So that means what? This is just put in the path where the current is flowing. What do you mean by current limiter? I am having a current that is flowing somewhere called I. I am simply going to insert my device here and ensure that the current is always less than my IDSS. What is IDSS? IDSS is this saturation current here for VGS equal to 0. So how do I ensure that? We'll go back to this circuit here and again try to understand. Now let us say for some reason this current starts increasing from 2 milliamperes to 3 milliamperes. So fine, I'll be on this part of the curve. Then more. The moment I reach IDSS, no matter whatever happens, can my current increase beyond IDSS? No. This circuit never allows the current to exceed 0 even though you increase the voltage across this, which is VDS. That means it now starts behaving like a constant current source only in this region. So this condition here for a current limiter is at any point, at no point of time will I have the current which is more than IDSS. It will limit the current to below IDSS. This is the behavior, or this is the functionality that we want for any current limiter circuit. Okay? So we have studied the amplifier, we have studied the multiplexer. Now we have studied the current limiter. So three again very simple devices, but huge in terms of implication, huge in terms of impact for limiting or enabling the proper use of signal circuits. So next, let's move on then. The fourth application, resistors, right? So it's always nice, you can always see that take any circuit, whether it be signal processing circuit or biasing circuit, whatever it is, you can never do away with resistors. Now, would it not be good enough if I can have a resistor which is a variable resistor? Okay? That's a beautiful thing to have. Okay? I do not have to be stuck with a fixed value of resistor. I can change the value of these resistors by simply changing the value of a control voltage, which in this case happens to be VGS. Okay? So now let's go back to this circuit here, a graph here. If you can see here, this is a particular graph. So can you tell me whether it is a transfer curve or a output curve? Yes, it is an output curve, right? Because it is a plot of VDS versus ID for different values of VGS. Now, as long as we are in smaller values of VDS, that is what we call as the ohmic region, right? As long as we are in this ohmic region, smaller values of VDS, you can see the shape of this particular transfer curve. It is very linear, okay? And you can change the slope of this curve by simply changing the control voltage at the gate. At VGS equal to 0, this is the curve. At VGS equal to -3, this is the curve. So we do have now two different set of resistors. Why? Because we have two different slopes for these curves. Now I have another question here for you, which we have already discussed in one of our previous sessions. Now, can someone tell me, is the resistance larger at VGS equal to 0, or is it larger at VGS equal to -3? Okay. So how to tell the answer? Do you take a guess or do you apply some concepts? Right? Before directly answering the question, let us apply some concepts. Now, at any point of time, what is the slope? The slope is given in this case. If you look at this particular curve, I'll go back to this and see. If you look at this curve, so the slope for this curve is this one. So delta ID divided by delta VG. Okay. So this I will call as slope at VGS equal to 0. Okay. Now next I take the slope for the last one, which is again delta VGS divided by delta IG. So this I will call it as slope -3. As you can definitely see here, the slope for -3 volt is lesser as compared to the slope for the one at VGS equal to 0. So I say the slope for this is larger. So does that mean the resistance is larger at VGS equal to 0? No, right? Why? Because slope in this case is delta I upon delta V. Okay, I'll rewrite that equation here, delta I upon delta V, which is essentially 1 upon R, right? Because R is V upon I. Therefore, if slope at R0 is larger, slope at VGS0 is larger than slope at VGS is -3, that would mean the resistance at VGS equal to 0 is less than the resistance at VGS equal to -3. Okay. So if you answered this, the answer was correct, but I'd appreciate it if you could explain this answer using this fundamental techniques of finding the slope and then telling. The slope is larger, but since resistance is inverse of the slope, the resistance is going to be lesser. So just by simply varying the value of VGS, we can get the different values of resistors, and hence we can call this particular MOSFET, this JFET as a voltage variable resistor. Okay. If you can also see from the graph, we can also operate it in the negative VDS voltage. Okay. So that we're not going to talk much about now, but it simply tells us that you can use it on the either side of the axis, and which enables you to connect it directly to an AC circuit without the need for biasing, and it will act as a small signal resistor for the AC signal. Okay, so then moving on, then what's the next application we can possibly look out for these JFETs? This one is called as the phase shift oscillator, right? Now before I say phase shift, let us understand what oscillators are. You can see the applications that we have taken up here. I am trying to give context wherever possible, so that we don't end up blindly understanding these topics. So it would help us if we know a bit of these concepts and understand it in that context, so it will be a much more beneficial experience for you all. What is an oscillator essentially, right? Any answers? As oscillator essentially is something which gives you a repetitive waveform, right? It could, if a particular oscillator gives you a sinusoidal signal, we call that as a sinusoidal oscillator. If it gives a square wave, we call that as a square wave generator, and so on and so forth. Anything which generates a repetitive waveform is called as an oscillator. Now there are certain conditions which satisfy oscillation, in the sense, if at all any circuit it is possible to do oscillations, it has to meet two conditions. Okay, we call them as Barkhausen criteria. I'm going to write that on the slide here. So let us see this, and how is it that we can possibly try and arrive at this one. So Barkhausen, the spelling is this way, BAR. Okay, Barkhausen criteria. So what does this basically tell? This basically tells you can have an amplifier or a transistor circuit or a FET circuit work as an oscillator provided there is a feedback mechanism, right, in such a way that the total phase shift around the loop, okay, the total phase shift around the loop, like a signal starts at the input here, a signal starts at the input, by the time it reaches the output, right, an entire path it takes, the total phase shift should be either 360 degrees or multiples of 360 degrees, okay, which we typically call as 2 pi radians. This is the first condition that has to be satisfied. Now are we able to satisfy that condition with this circuit? The answer is yes. How is that? The JFET that we have here, it provides an inverter, right? It provides an inverting sort of a behavior, in the sense the input, if you apply as an increasing input, the output becomes decreasing. That's what we call as a phase shift of 180 degrees. So the transistor stage gives here a phase shift of 180 degrees, and then we have 3 RC circuits, right? RC, RC and RC. So this together combined, they are going to give us so together combined, they are going to give a total phase shift of 360. Can we pause? Barkhausen criteria, so it has to provide an overall phase shift of 360 degrees. So 180 is provided by the device here, and the remaining 180 is provided by 3 sets of RC circuits, which overall provide 60, 60 and 60 degree phase shift, making it a total of 360 degree phase shift. Then what is the second criteria? The second criteria is, we call something as the loop gain should be unity. So what do you mean by the loop gain? Now any transistor has a gain, we call that by a value of A, and the feedback network has also a factor of gain, which is usually a truncating one, and we call that as beta. So the magnitude of this loop gain should be unity. So if we are able to satisfy these two conditions, then we can say that oscillations will happen and this circuit will behave like an oscillator. So the two criteria have to be met, and then it becomes an oscillator. So this is how you can use JFET as a phase shift oscillator. Now let's move on then to see the next application. So next application is a CMOS inverter. So we have, to sum it up, we have seen many applications for JFETs, starting from amplifiers all the way up to oscillators. Now let us embark upon a new set of circuit technique, to the extent we start calling them as devices, we call it as a CMOS device. Now what is this CMOS device? Now CMOS device, as I already told, it nothing but complementary metal oxide semiconductor. So if you can see this construction here, what we are trying to show is the construction of a simple CMOS inverter. Now what this inverter is going to have? If you can see here, at first glance it appears as a very complex sort of a circuit, but that is not the case. It's a very straightforward and the simplest possible circuit you can have. Now what do we have here? We have an overall N-type substrate, and then we have a P plus here. So this is your PMOS. Okay, it's a short form for P-type enhancement metal oxide semiconductor field effect transistor. Then we have a P-type well, which is just like a P-type substrate, into which you are going to fabricate one N-type device, which I am going to call as NMOS. So what do you have now? You have one circuit where you also have a P-type device and you also have a N-type device. Overall, we now call this as a CMOS device. Now how are they connected in case of an inverter? In case of an inverter, the gates of both the devices are shorted and become your input terminal Vin, and then likewise the drain terminals are shorted and they become your output terminal. As I said, it's a very simple arrangement. Two devices, short the two gates becomes input, short the two drains becomes output. Then what about those sources? No, we are not going to short those two. We are going to connect the source of the PMOS to the higher potential, okay, which is over here given as VSS, which simply means it's a voltage connected to the source. Unlike what we called as VDD earlier, it was connected to the drain. And the source of the other NMOS device is then connected to the ground or the lowest potential you have in a circuit. Now since we all knew MOS devices are 4-terminal devices. So which is the 4th terminal? Yes, you guessed it, that's a substrate connection. So where is the substrate connection going? The substrate connection is the bulk connection for PMOS here, and it's a bulk connection for NMOS here. Now these two are shorted to the source, and we essentially use them like a 3-terminal device, just like we've been doing it. Now this is how the overall fabrication of a CMOS device looks like. That being the case, how would the electrical circuit look like, and why is it that we are connecting these two devices in this fashion? Let us see it in the next slide. So this is the actual symbol arrangement for the CMOS device. What do I have? I have the two gates connected, and they becoming your input. I have the two drains connected and they becoming your output, and the source of the PMOS connected to the highest potential, which is VSS, and the source of the NMOS connected to the ground. And we are using it as a 3-terminal device, so we short the substrate and source connections of the two devices respectively. So this is a circuit, and why is it that we call this as an inverter? To understand this phenomenon, let us go back to the board over here and try to see how this circuit actually functions, and why is it such a versatile circuit, and why is it that we keep using this to do the inversion. So this is how I am going to show these two devices. This is your enhancement device. So I am going to show the PMOS type, right? So at the top you are going to have the PMOS type. So you are going to have the arrow mark outside, shorting it to the source terminal. This is going to be the drain. This is going to be the gate connection. So this is the gate, the source and the drain of your PMOS device. Likewise, let's short this drain to the drain of your NMOS device. And what does an NMOS device have? The NMOS device has the arrow mark pointing inside, and that is shorted to the source, the substrate connection, and that in turn is given to the ground. Whereas this is connected to VSS, okay, the gate connection here, and these two are shorted, and that becomes your input, and the two drains shorted becomes your output. Okay. So this is essentially your source, drain and gate. This is again your drain, source and gate. Now what is so special about this circuit? So let us apply a pulse voltage. What is a pulse voltage? A square waveform, right? Okay, which we typically call as voltage level 0 volt and voltage level, it could be 5 volts or whatever is the logic high, which is VOL and VOH. To make things very easy, we also call this as logic 0 and we also call this as logic 1, because in digital circuits we only have two levels, logic 0 and logic 1. So let us see, if this is the input that I give, the output should come inverted, in the sense what? Whatever is the input here, the output would be inverted. In the sense, if the input is logic 0, the output should be logic 1. If the input is logic 1, the output should be logic 0. Now how does this circuit work and why is it so special? Okay, so let's try and analyze this particular component. So whenever V in is 0, so what happens now? That 0 volts is connected to the gate of both the devices. So VGS here becomes 0 volts. So if VGS is 0 for a NMOS, then this device is going to be off, right? Because for a NMOS device, we need to have VGS larger than VT. Typically for a 5 volt device, VT could be around 2 volts. Likewise here, the voltage that I am applying here, I need to find out what is my VGS. Okay, the VGS is nothing but the difference between the gate voltage here and the source voltage. Now the source is at VSS, which could typically be, let us say, around plus 5 volts. The source is at 5, and if the gate is at 0, so difference between those two is 5 volts. But is it a positive gate voltage? No. VGS is nothing but what? We already done this, VG minus VS. Now what is VG? VG is 0, because I am applying 0 volts now to start with. So it is going to be 0 minus 5, which is minus 5. Now remember, for a PMOS device, all the voltages and currents are reversed. So if a NMOS is off at VGS equal to 0, PMOS would be on at VGS equal to minus 5 volt. Okay, if VGS becomes 0, then PMOS would be off. So this device is on and this is off. So if this is on, what will happen? The output current will flow through the PMOS device and then reach the output, and thereby I get logic level 1. So the input is 1, the output is 0, the output is 1. But then you may ask, what is so special about this? The most special feature about this is, while this is happening, there is no connection between positive of the source and the negative here. That means you do not have any current flowing from here to here, or there is no crowbar current which flows from here to here. That means once you have an output capacitance here, for example, if I have a load capacitance of CL, once the capacitor charged to the full voltage of 5 volts, then no current flows in the output. That means what? The moment this charges to VOH, which is plus 5 volt, the output, then the current stops. So you establish the logic level at the output, current stops means what? There is no power consumption. So we call CMOS devices as those devices which have zero static power dissipation. So that's a basic feature of any CMOS device. Now let us quickly analyze what happens if we change the input from 0 to 1 volts. If you change it from 0 to logic 1, let us say I now give it 5 volts. So if I am giving it 5 volts, what is essentially happening? I am ensuring that my VGS at the NMOS is larger than VT, which is around 2 volts. So this device is on, but now if you check here, what is the VGS now? This continues to remain at 5 volts, whereas this has also gone to 5 volts. So your new VGS would be 0 volts. So if the new VGS is 0, then this device is off. So then this device is off, this device is on. Then if the output voltage is high, all it has to do now is it discharges through this NMOS device. So the capacitance discharges through the NMOS, ensuring that it reaches the logic 0, okay, 0 volts. While this is happening, there will be a discharge current flowing. Once it is completely discharged, again no power dissipation. Why? This is anyway off. Even though this is on, I have nothing left to discharge, because once this is 0, both are 0, no current flows from output to the ground. So again I am ensuring that the static power dissipation is 0 or very negligible if you ignore the leakage currents you have through the bulk or substrate. So that is a speciality of a CMOS device which we are now used very widely across the world. Now, is that the only reason why we are using CMOS devices? The answer is no. There is much more to it than meets the eye. Okay, I'll just add one or two more topics, one or two more points which go in favor of these CMOS devices. Nowadays, entirely all the applications or all the devices, all the microcontrollers, all the processors, all the Intel chips, whatever you take off, they are all built using this technology. Invariably you have equal number of NMOS and PMOS devices. For example, if it were to be a 2-input NAND gate, or if it were to be a 2-input NOR gate, then you're going to have 2 NMOS devices and 2 PMOS devices. So invariably for all the devices you're going to have equal number of P and N, ensuring that it is a complementary device where NMOS and PMOS complement each other. They take turns to either charge or discharge an output load, thereby ensuring the transition in the voltage level from 0 to 1 volts. This also enables a large packing density. That means what? You can shrink the device even further, which you could not possibly have done earlier. This was evident in the construction slide that we showed, wherein you can pack these two devices very close to each other when you want to fabricate. Not only that, these CMOS devices have a very high level of noise immunity, in the sense that they can withstand the noise to a large extent, and not only that, because of their smaller size, they do tend to be much more faster. But they can't be as fast as the BJTs, which I already told. That is one drawback which we usually overcome using a combination of the CMOS devices as well as the BJTs, which is basically called as bi-CMOS drivers. So with that, we have more or less completed this particular session. So let us go back and summarize what is it that we have done in this entire session. Okay, so we started this session, okay, by seeing the various applications. Okay, and we basically saw the application using the JFET, which is as an amplifier, as an analog switch, as a multiplexer, as a current limiter, as a voltage variable resistor, and as a oscillator. Finally, we saw one example of a complementary device which is called as a CMOS inverter. Now before we wind up, let us try to see whether we do have some gaps to fill with. So I'll ask some questions, so let us see whether you are able to answer that. Now the first question I'm going to ask is, in the application of voltage variable resistors, which is the region I am operating my JFET in? Okay, I'll repeat the question. In the voltage variable resistor example or application, under which region am I operating the JFET? So what are the two options? It can either be the ohmic region or it can be the saturation region. So the answer is right. The answer is ohmic region. Why? Because whenever the VDS is very small, that is when we have a linear relationship between V and I, which ensures that I am in a resistance region. There was a hint there in what we said as ohmic region. Okay. And the second question that I am going to ask is, in a current limiter, will the current be limited to above IDSS or below IDSS? In the sense, suppose I am having a circuit which is being used as a current limiter. So will the current at any point of time be less than IDSS or more than IDSS? Okay. So the answer is, it will not allow the current to go beyond IDSS, which is nothing but the drain saturation current when VGS equal to 0. And do I have a limitation for multiplexers? Like, can I use only 2:1 multiplexer or only 4:1 multiplexer? Do I have a limitation? No, right? The example that we took was, we can take as many number of inputs as we want and have a n:1 multiplexer. Just ensure that only one input is channeled to the output at any given point of time, whereas the rest of the inputs are simply cut off by turning that particular JFET off. So the final question here then would be, if I want to turn the JFET off, should I make VGS 0 or should I make my VGS minus 5 volts? So what can be the possible answer for that? If VGS is made 0, will the device be on? Okay, so the correct answer is, if VGS is 0, the device would still be on. If you want to make the device off, we have to make VGS much less in the negative side, thereby so that ensure that we reach the pinch off region and eventually go and cut off the particular device. And finally, one last question about the CMOS inverter. Does CMOS inverter have equal number of P-type devices and N-type devices, and are they enhancement or depletion? Yes, the answer is both the PMOSs and NMOSs are equal in number in a fully complementary CMOS inverters, although we do have, or CMOS circuits, although we do have cases where we only have one NMOS, rest all are PMOSs and vice versa, but those are all special type of circuits used for other applications. So with that, we are going to conclude this particular session wherein we studied the various applications of FET, and we followed it up with studying a special type of arrangement which we call as a CMOS inverter. Thank you.